that?
Because it says chapter 8 on the thingy. So is it kind of chapter 8?
Well, this was chapter 8 from a different book. That's why it says chapter 8.
Wait, do you make these subjects?
Yeah.
No, because I don't know, there's some ways to just take it out on people.
Yeah, they take it from me. That's why I put my name on
Do you
it.
have these problems yourself?
No.
Or do you find them somewhere?
No, I steal them from someone else.
And then he stole it from someone else.
And then someone else steals it from me.
So we need to find the
Yeah, this
original
one's
study
formatted really
guide.
nicely, so I would say
Yeah.
taking the-
Well, that's my genius, is formatting it nicely.
No, it looks really good.
Thank you. I spent a lot of time at Barnes & Noble's making these look nice.
I appreciate it.
Rip Barnes and Nobles.
Yeah.
Oh, yeah.
An endangered species now.
They closed the Santa Monica one down a couple days ago.
Okay, so we got the first one is estimated. We're saying X. Sorry, X is a binomial distribution. We've got 12 trials. Probability of getting a frozen chicken. Oh, sorry, a salmonella chicken is 0.3, which is not good. Delicious salmonella.
So one in every 3 chickens will have salmonella.
So we want to know the probability that, well, it says greater than 6. So I think common misconception is to start with 6, but you really got to start with 7. Okay, so it's got to be 7 is greater than equal to X is greater than equal to 12. And that just comes straight from the calculator.
Well, you could also just write the greater than symbol, right? After 6.
Greater than 12, yeah. Strictly greater than 6, yeah. You could have written it that way. But the reason why I like to write it that way is because, yeah, so that it comes into the calculator really nicely. So the calculator is always going to be greater than or equal to. So you might as well just use that. So what do we say, 7 to 12?
Thanks, Carly.
So 0.386.
Oh, that door. I mean, that.
That door.
There you go.
That's what I did.
Was it somebody? Hey.
I'm seeing it from the screen. And I don't know if you know that she has a card where she puts all her side. Well, we just did that.
Oh, yeah.
No one dream if you have a key.
You're going to put the card back?
Yes. Hey. Yeah, I can.
Thank you.
That's Carly's
Get your man. Somebody, please come to
Okay,
us.
number 4.
Okay, let's see. Number 2, probability that a certain machine will produce a defective item is 20%. That's a really bad machine. If a random sample of 6 items is taken from the output of this machine, what's the probability that there will be 5 or more defectives? So really this is pretty much the same problem. The only difference is the parameters here. So we're saying we have 6 items. 6 items. Probability of getting a defective one is 0.2. And we are interested in the probability that we have 5 or more defective items. So that's 5 is less than or equal to X is less than or equal to, in this case, 6. And that's the same kind of a calculation. So if we come back here again, and we do that. Oh, no, we got to start over again, don't we? Yeah, don't do that. We have 6 trials, 0.2. So we want to go 5 or 6. That's 0.0016. 0016. Okay, 3. Now 3 was a weird one because if we do this, we're saying 50. Okay, so we have 1,500 adults who support an increase in sales tax. The 5% to 6% is there to confuse you. You're not actually using 5% or 6%. With additional revenue going to education, let X be the number in the sample that say they support the increase. Suppose that 40% of all adults in Ohio support the increase. The probability that X is more than 650 is, okay, so we have a random sample again. And our random sample has size 1,500. That's a big sample. And the probability that somebody supports that is 0.4. So now we want to know the probability that we have more than 650. So that I believe that starts at 651. Excuse me. And we go to 1,500. All right, so let's calculate that. We're going to quit from here. We'll do this again. 1,500, 0.4, and we want to know 651 to 1,500. You get 0.004. So what makes this one confusing is that that's not the way the answers look.
So I want to call you Eddie because she's like, you can give Eddie the money, but...
No, she doesn't.
No? Okay.
But you can give me the money if you like.
Do you know who Edwin is? No? Okay, well I'll just call her right now.
Okay.
Thank you.
Be Edwin in our class?
I don't think it is.
No, like a teacher? Well, Tucker's first name is Edwin. Tucker? He's in B building. What is it? 10.
I don't think it's the Tucker, though.
Well, I don't know.
I mean, if it's,
I'll figure it out. Thank you.
yeah. Okay, so we have between... Okay, so we have to figure out 0.004. Is 0.004 less than 0.0001? No, it's not. Is 0.004 less than 0.001? No, it's not. Is it less than 0.01? Yes. C is the correct answer. 0.996, that's not correct, and none of these, no. The one that best fits here is C. Okay, so C because 0.004 is less than 0.01. Okay. Okay, so from here, I think, let's just see. Is there which ones do you want me to do? Do you want me just to go through all of them, or what do you want to do? Yeah? Just go through them?
We do number 6, actually.
6 for sure, okay. We'll get to 6. I'll do 4 first, though. Suppose we select an SRS n equals 100 from a large population. Okay. Let X be the number of successes in the sample. We want, for which value of P would it be safe to assume that the sampling distribution is approximately normal?
Sorry. By any chance you have an envelope? Or can we have?
I might. I do.
Thank you.
Okay, so for a binomial distribution to be approximately normal. Okay, 2 things have to be true. Number 1, NP has to be greater than or equal to 10. And number 2, n times 1 minus p has to also be greater than or equal to 1, 10. Okay. And what this does is NP is the mean of the binomial distribution. And when we have the mean of the binomial distribution, there's going to be a peak. So what this says is we want the peak to be at least 10 units away from the y-axis. And we also want the peak to be 10 units away from n, basically. So we want it to be somewhere near the middle. And we want the peak to be somewhere near the middle so that our distribution won't be left skewed or right skewed. Okay, so what we can say is these conditions ensure the single peaked distribution is not skewed. Significantly. You don't really have to know that. You just basically have to make sure you get all these right. So let's see, that first one is n times p, so we have a sample size of 100. 100p should be greater than or equal to 10. So that logically leads us to say that p should be greater than or equal to 0.1. The other one says that 100 times...
It's close.
It's close?
Yeah. Thank
Okay. Times 1 minus p, that should also be greater than or equal to 10. And that leads us to believe that p should also be less than or equal to 0.9. I'm kind of avoiding doing the algebra right now, but if you did the algebra, you would get those results. So, any answer that would have been between 0.1 and 0.9 would have been correct. Since this was a multiple choice question, this was a multiple choice question. And 1/9, which by the way, 1/9 equals 0.1111. Was the only answer choice that worked. In an actual answer, short response question like this, you could give me any number between 0.1 and 0.9 and it would be correct. That's where we have 0.9. Okay, should we look at 5? Yeah? Okay. Well, right off the bat, we have, cards being selected of a deck of 52, right? And that's not a lot of cards to pick from. So we have to make sure that for the probabilities to remain the same, in this case P, the cards need to be replaced. Okay. So that has to be part of the answer choice. Otherwise, we're not going to have a normal distribution because P keeps on changing every time you pick a card. So the only thing that really has that in it is C. If you read C, it says Y is a binomial distribution with 40 observations and a probability of success of 0.5, provided that the selected card is replaced in the deck and the deck is shuffled well. Oh, we didn't even think about shuffled well, but that sounds like it would make sense. Otherwise, you get black card, black card, black card, black card. So yeah, C should be it. Should be the correct answer. 6. In a certain large population, 40% of the households have an annual income of over $70,000. A random sample is taken from 4 of these households. So I'm going to stop reading right there and I'm going to say N is 4 because you're only looking at 4 households. I want to write that down before I continue because I'm going to get confused with all these numbers. Okay, let X be the number of households in the sample with an annual income of over 70,000. So what's the probability that we have annual income over 70,000? 40%. So that tells me now that P equals 0.4. Okay, do we qualify as a normal distribution? Do we have a set number of trials? Yes. Is the probability of success always the same? Yes, it's always going to be 0.4. Are the trials independent? Well, we don't really have an indication, but we can pretty much assume that it's going to be independent. Are we interested in the number of trials that are successful? Yes, we are. So we're saying that we have a binomial distribution with 4 trials and a probability of success of 0.4. We want to know the mean of the sample. So mu, that's going to be equal to NP. And that's going to be equal to 4 times 0.4. That's 0.16.
I think it's 1.6.
1.6, yeah, you're right. I'm going to replace mu. Ooh, that's weird. There we go. That's our mean, 1.6. 7, we have the probability that a 3-year-old battery works is 0.8. Okay, that could be P. P could also be 0.2 depending on what I see when I keep reading. A cassette recorder requires 4 working batteries to operate. The state of the batteries can be regarded as independent, and 4 3-year-old batteries are selected for the cassette recorder. Okay, so that does sound binomial now. X is binomial distribution. The probability of success was 0.8, and we're selecting 4 batteries. So we want to know what's the probability that X is exactly equal to 4. You could use a formula. I don't recommend you use a formula, but there is that. For choose 4 times, what is that, 0.8 to the 4th power times 0.2 to the 0th power. Or you can just use your calculator, of course. That probably would be the way I'd do this. In any case, what is that? 16 times 16 is 0.0256? No. 64 times 64.
0.4096.
0.4096. How would we do that? I say that every day to the freshmen. Okay, that brings us to 8. We have 2% of the circuit boards are defective. That's not bad, but that's still not great. Circuit boards are randomly selected for testing, and the number of circuit boards inspected before a defective circuit board found is greater than 10. The probability that the number of circuit boards inspected is greater than 10. So really what that means is we're going to inspect 10 boards, and they're all going to be working, or non-defective. That's really what we're saying. After those 10 boards, it doesn't really matter what happens. Maybe the next one will be defective, maybe not. As long as we have the first 10 are working, then the first working board or the first effective working board, or the first effective board will have to be after the 10th one. So 10 working ones, that's 0.98 to the 10th power. And I think I got to do this if I want it to work. That's an 81/71 probability. Okay. Feeling good about the first half of this? I hope. Second half. Okay, so according to the government data, 20% of employed women have never been married. Okay, I'm trying to think if that would be true. That doesn't seem true. What's the random variable of interest here? Well, I don't like this question all that much because actually there's a lot of things that it could be. But we could say that x is equal to the number of employed women who have never been married. Okay. There could be a whole lot of other things that x could be, but I think this is the one that we're looking for. Is x normal, binomial, or geometric? The truth is we don't know what distribution we're looking at, since we don't know the question. That's the truth. We don't know what they're asking for, so we can't tell you what kind of distribution that is. What does the answer key say? Neither.
Yeah.
Good. If we knew the question, we could probably answer that a little bit better. So, let's move on to questions. Number 10. If 10 employed women are selected at random, okay, so now that sounds like it's going to be a binomial distribution because we have a number of trials. The hell is a bitva? And I thought I had my do not disturb on. Yeah, I do.
How's that even showing up?
It does not that program that does not respect my quiet hours. Horrible program. 10. 10 employed women are selected at random. What's the probability that 2 or fewer? Okay, so that sounds binomial now. We're 10 and 0.2, and we just want to know the probability that x is 2 or fewer, right? So don't forget 0 is a perfectly good response. Two or fewer, right? Yeah, 2 or fewer. And I don't know what answer you get from that, but this says 0.6778. Again, use the calculator program. 11. What are the mean and standard deviation of x? Okay, so x as we have it, as in number 10, mean is going to be equal to 10 times 0.2. Okay, standard deviation, that's going to be equal to what is that? The square root of 10 times 0.2 times 0.8. $1.2645. Okay. That should take care of for number 11. Number 12. Find the probability that the number of employed women who have never been married is within one standard deviation of the mean. Okay, that's great, but you have to remember that when you hear standard deviation, your head usually defaults to normal distribution. Okay? It shouldn't. This is a binomial distribution. Don't use normal CDF. So within one standard deviation, that means greater than, the mean was 2, standard deviation is 1.265, and less than 2 plus 1.265, so it's somewhere between those two numbers. So we want to know the proportion that's between 0.735 and 3.265. Basically, that's x equals 1 plus x equals 2 plus x equals 3. But you can definitely put those numbers into your calculator as a and b. Actually, let's do that. No? Let me look at it when I do this, okay? Binomial, we have 10, right? And 0.2. And greater than 0.735. And less than 3.265. 265. That gives us 8971. What is the answer key saying?
60%.
Yeah, it treats it like a normal distribution.
I guess.
Treats it like a normal distribution? Those bastards. Obviously the sample, okay, so the answer key doesn't make sense. What number did I just get? 0.91. Note. The answer key does not make sense. Okay. Because the sample size isn't greater than 50, right? Yeah, if it was over 50, you would be able to do that. Because, no, because NP would be greater than 10. 0.2 times 50 is 10.
Until the first success.
Yeah, do you understand where that 50 came from? That's like, NP has to be greater than 10. Okay, so let's get to 13 then. Describe 4 conditions of binomial setting. What was that? Number 1, set number of trials. What? A set number of trials n. 2, 2 outcomes, success and failure. Number 3, probability of success is P for all trials. And 4, did I mess this up? And 4, what is this? All trials are independent.
Thank you.
So those are the 4. You should be able to kind of bust out with all 4 of those at any given time. All right. 30 students in a particular... sorry. Let's read this bold part here. A survey conducted by the Harris Polling Organization discovered that 63% of all Americans are overweight. I have a friend who lives in Texas, and whenever he visits here, he says, "Y'all are so thin over here." Literally, y'all are so thin over here. It's funny. He was also kind of weirded out that I drove with my window down.
Wait,
I was driving, because I was driving like, we were taking PCH. I was driving, through Santa Monica or whatever, or Malibu, and I had the window open. He's like, "It's so weird. We don't drive with our windows down ever."
Because it's too hot there.
Like, why wouldn't you drive with the window down? Like, if you're on the PCH in Malibu and your window's not down, or if your top isn't down, if you have a top, you're kind of wasting your money, right? Yeah. That's why you live in California.
Traffic. You're just kind of stuck there for like an hour.
No, still good. Okay, it could be raining, but that happens like twice a year. So.
2 days.
We already had those 2 days.
Cheers, thank God.
Okay, 30 students in a particular adult Sunday school are questioned about their weight. Assuming this is a good cross-section of Americans, show that the conditions for the binomial distribution are met. Okay, so let's see. Number 1, is there a set number of trials n? Yes, we are only looking at 30 students. So n equals 30. So that works. Condition 1 works. Condition 2. 2 outcomes, success or failure? Sure, 2 outcomes. Overweight and not overweight. 3. Probability of success remains the same. And yeah, so for each adult Sunday school student, P is equal to, what is that, 0.63? Ugh. Lastly, all trials are independent, and this is a tough one to actually show in this case, but this is one of the ones that we would have to kind of assume that the probabilities are independent. Okay, so we'd have to say weights must be assumed independent. I think, if you have like people, let's say we had 2 people from the same family, there's a high probability that either they're both overweight or they're both not overweight. So they're not actually independent depending on the way that the sample looks. Does that make sense for the independence? So that's one of those things we're just going to have to assume. And that's going to be our problem for the rest of the year. Okay, find the probability that 18 or more of the students in the Sunday school are overweight. So that should be pretty easy. First thing we want to do is we want to say that our x is a binomial distribution with 30 and 0.63 as our parameters. And now we want to know what's the probability that x is greater than 18 and less than 30. And you can get that from the calculator. I'm going to read that as 7055. I'm going to assume that that's true. Yeah. Okay. 16. Can a normal approximation be used for the sample n equals 30? Well, let's check. NP, n was 30. P was 0.63. That's equal to 18.9. So yeah, that's greater than 10. Okay. How about the other one? N times 1 minus P. That's equal to 30 multiplied by 0.27. No. This is less than 10. Is it 0.37? So I messed up. Thanks. Okay, so that's greater. This is greater than 10. So yes, the normal distribution to approximate. Okay, so in order for us to use a normal distribution, we're going to need to know our mean and our standard deviation. So mean is equal to NP, which equals, we just computed that as 18.9. Standard deviation, that's equal to the square root of n times p times 1 minus p. Which is equal to the square root of n, where that was 30, p was 0.63, 1 minus p is 0.27. That gives us a standard deviation of 2.259. Was that? 0.3? Damn it. You're right. 2.644. Okay, so a binomial distribution with 30 and 0.3, that's approximately equal to a normal distribution with a mean of 18.9 and a standard deviation of 2.644. Sweet. All right, so we want to normalize 18, I think, because we want to know 18 or more. So what is my z equal to? Z is going to be equal to 18 minus 18.9 divided by 2.644. It's negative 0.304. So that means that the probability that x is greater than 18, remember that greater than 18 is the same thing as greater than equal to 18 in a normal distribution setting. That's the same thing as the probability that z is greater than negative 0.340. That's a normal CDF calculation. Let's get to the calculator. Normal CDF calculation would be norm CDF. And I already forgot. Negative 0.340. Wait, 0.34. No, 304. 304.
Yeah.
Okay, to 1E99. Good. 0.6194. What is it? Why is it different?
Because they use 3.3404 instead of 0.340. You gotta plug in.
Yeah. Negative 0.34. Oh, okay. Wait, what did I do? Oh, it's point. Wait, am I wrong or is this wrong?
3.404.
Is this wrong or is that? Yeah, it's okay.
No,
You did it wrong.
You put 0.304, it's
40.
Just like added a 4 and
340 like that. 6331. Okay. There we go. 6331. I mean, this is an approximation. Notice that it's not actually all that great. 0.75, 0.63. Not that great. Results may vary. Okay, how many Americans would you weigh before you encounter the first overweight person? I think the answer is 1. Any case, this is the mean of the geometric distribution. Is asking for the mean of a geometric distribution. And mean equals 1 over p, which in our case is 1 over 0.63. Yeah, 1.58. So it's either the first or second person is probably going to be overweight. Probably higher or lower depending on where you're taking your sample. What are supposed to be some really fit cities? Like Denver or something like that, maybe?
Colorado.
LA?
Maybe parts of New
I
York,
heard something
there's
like
a lot
Wisconsin. Wisconsin's supposed to be crazy too. Yeah.
more Denver. I mean,
18.
New
Yeah.
York, they walk
Oregon
everywhere.
is not a city. New York, you know,
Because they walk
because they walk a lot. They get their 10,000 easy.
Yeah, like same thing in Italy, like everybody's super fit there because they walk all the time.
They eat pasta all the time. All those carbs, and they're still
Everybody in Europe is like really skinny.
Because they walk like everywhere.
because their portions at the restaurants are so small.
Small, just regular.
Yeah, I only go to all you can eat, so.
There you go. I think they have a whole website. This is why you're fat. It's because you're only going to weigh. Okay.
That's me right now. Okay,
I'd like to go to all you can eat right now too. KBBQ sounds good.
Good
it
dog.
always sounds good.
18. What's the probability that it takes more than 5 attempts before an overweight person is found? Okay, so we're basically saying that the first 5 people we look at are not going to be overweight. So the first 5 people we check are not overweight. So basically this is going to be, what is that? Not overweight is 0.37 to the 5th power. There we go. After that 5th person, it doesn't matter what happens. We just have to make sure that those first 5 people are not overweight. 19. Construct a cumulative distribution table for the number of Americans weighed before an overweight person is found. Okay, so we want to stop at n equals 6. Let's see, what's the probability that x equals 1? That's going to be equal to 0.63 because that first person was overweight. What's the probability that x equals 2? That's going to be not overweight person, 0.37, followed by an overweight person, 0.63. Probability that x equals 3. That's going to be 2 not overweight people, and then followed by an overweight person. Probability that x equals 4. This gets tedious really fast. Oops. That's going to be to the 4th power times 0.6, no, 3rd power times 0.63. Probability x equals 5. That's going to be 4 overweight people, followed by 1 not overweight person. Probability x equals 6. That's going to be 5 not overweight, followed by 1 overweight person. There we go.
The answer keeps so different.
Does it? What does it say?
Like for 2, it's 0.86.
0.86?
And for 3, it's 0.95. It just keeps going up.
Oh, it's cumulative.
Oh, yeah, but it's still
Because it's cumulative. Okay. So
Oh,
this is way too much. Cumulative.
God.
We're supposed to do this in power.
So the probability x equals 1 equals 0.63. The probability that x equals 2 is equal to 0.63 plus 0.2331. Probability that x equals 3 is going to be equal to 0.8631 plus 0.0862. Looking good?
Yeah.
Probability that x equals 4, that's going to be equal to 0.9493 plus, where did I leave off? 0.0319? 98%. Probability x equals 5. That's equal to 9812 plus 0.118. Oh, I have too many zeros here. There we go. And then the probability x equals 6. That's going to be 0.993 plus 0.00444. There we go. That's my distribution. Okay. Anything else from chapter 8, the chapter 8 one?
So quick question.
Yeah.
Why can we assume the first person was overweight? And just because it's...
Because we don't know.
Oh.
Yeah.
Okay.
Maybe he is, maybe he isn't. 63% probability that the first person will be overweight.
Tedious.
You have to have a good double.
Okay, so the first one that you were given, the one that says chapter 7. Anything from that first page you want to look at? Absolutely. Okay, so chapter. Okay, so number 5 we're saying. Okay, the weights produced in a certain department follow a normal distribution. Mean is 60 and standard deviation is 12. So they're saying that X is a normal distribution with bye-bye 60 for the mean and a standard deviation of 12. So we want to know the probability that X is less than 45. Okay. So to me this just sounds like using the normal CDF function on the calculator. So let's see. Let's normalize. So Z is going to be equal to 45 minus 60 divided by 12. So that's going to be the same thing as a probability that Z is less than negative 1.25. What was the answer on this one? 1056? Maybe?
Yeah.
For number 5?
I remember it.
5B 1056.
For problems like that, do we have to find the z-score?
If it's multiple choice, no.
Okay, but
If it's free response, you will get points for showing the z-score. Okay. Is everyone okay with how to do this without showing the z-score? Yeah. Yeah.
Can we do number 8 on the free response?
Yeah. 8 on the free response. Okay, so that was that one with the venti and the grande, right? Okay, so the mean and standard deviation. So the mean here again, you just add the means together. There's nothing magical about the means. The only thing that's strange is the standard deviation, and because it's a standard deviation, you have to go through the variances. So the very first thing to do is calculate the variance for the grande drink, calculate the variance for the venti drink, which we do over here, and then we add them together. So our two variances added together give us 1.2864. Once we have that variance, we can square root it to get the standard deviation. So that square root of that standard deviation is 1.1342. That gives us a distribution with a mean of 7.8369, standard deviation of 1.1342. I'm going to pause here and make sure we understand how to get all that. Yes? No? No. Okay. Which one? Mean or standard deviation? Standard deviation. Okay. So let's take a look at the first one, and let's get the variance for the grande drinks. Okay. So the variance for the grande drinks is going to be equal to, well, you get the standard deviation for the grande drink is 0.8270, right? So the 8270, have a nice day. You square that, and that gives you the variance for the grande drinks. It's 0.6839. We're going to do the same thing with the venti drinks. The standard deviation for the venti drink is 0.7762. You're just going to square that. 7762 squared. That gives you 0.6052. So if you want to add the grande drink together with a venti drink, you just have to add those two variances. Sigma of grande plus variance, grande plus venti, squared. Okay. That's just equal to 0.6839 plus 0.6025. That gives us slightly different results.
It's not point. It's 0.6839, not 69 for the
Which one?
calculation.
Oh, right here is 39.
There you go.
That gives us the same thing. That's good. And then from there, you just square root that, and you get that's our standard deviation. Square them, add them together, square root.
So when you square it and add it together, that's just the variances added together?
Yeah. When you square standard deviation, you get a variance. Do we need to go further with number 8? No, we're good. Okay. Anything else? All right. I'm going to shut off the recorder and upload this to YouTube's.